Bernoulli's principle is the concept that an increase in a liquid's speed creates a pressure decrease, and a decrease in a liquid's speed creates a pressure increase. Here are some examples. Submarines lifting out of the water. Curveballs thrown in baseball. Airplanes moving through the air.
Hi guys, it's me and I'm here with my dad.
Hi.
And we're talking about Bernoulli's principle and his equation and examples, and one of the things we thought about was airplanes, but then we also thought about submarines, and my dad just happened to be a submariner.
Hi, how you doing? Most people tend to associate airplane, usually the wing of an airplane, with Bernoulli's equation, which creates lift and helps airplanes fly. But submarines kind of fly under the water, ignoring other things that create lift, like temperature of the water, creating density and buoyancy factors, as well as the amount of water that we have in our ballast tanks. We also use Bernoulli's principle when driving close to the top of the water. How submariners tend to think of Bernoulli is that mass flow rate is equal, this is basic equation, density, which is this funky looking P, times area, which is a capital A, times a little v or vector, which is speed. For a given mass flow rate at the start of a point to the end of a point, if the mass flow rate, or the amount of water passing by at a time, is equal to density, which if we think remains constant, times area times speed. And if the area decreases, then to keep mass flow rate the same, since density doesn't change, the speed would also have to increase. So if we have a nozzle and we decrease the area or the size of that nozzle, like putting your finger over a hose, that creates speed of the water. Okay? Now, if the speed increases, then pressure will decrease because there's less force or pressure exerted to the sides of the container or the nozzle. Okay. So Maddie, can you help me with the sub, please? Okay. Here's an example. This yellow ruler is the top of the ocean, and if the submarine is just driving underneath, this area and this area is relatively the same. Okay? But sometimes submarines might get a bit heavy, and so what they do is they put an up angle on the ship. Now the boat would not come to the surface, but what we'd be doing is using our submarine as a wing. So if you take a look at the area out here, there's a large area, and here there's a small area. So if the mass flow rate here is going to be the same here, and density doesn't change, here you have a large area or a lower speed, and as the water flows through here, now suddenly you get the seawater picking up speed over the top of the ship as compared to the bottom. So as the speed picks up here across the top of the ship, if the speed increases, the pressure
Decreases?
The pressure decreases. So now you have a lower pressure region here on the top of the ship. You have a higher pressure underneath, and essentially it's pushing the boat up. And what's actually holding the boat down underneath the waves is a combination of speed, buoyancy factors like I mentioned with the tank, with the water in the ballast tanks, and also the temperature of the seawater. So a lot of times we'd come up and we'd want to get sensor arrays or maybe a periscope up above the water. We'd put an up angle on the boat and we'd essentially drive just like that right across underside of the water. And that's what we used to create lift with Bernoulli's equations and submarines.
Alright, thanks guys.
Here we have my brother blowing air between the cans, causing a change in pressure and having them switch positions. They moved a total of 6.5 inches forward. Here we have a video of me putting a ping pong ball over the moving air coming out of a blow dryer. The ball levitated in the air because of Bernoulli's principle. It went up to 21 inches high and started at 0 with a range of 21 inches. Now the ball changed height because of the different pressures coming out of the blow dryer. Here we can see Bernoulli's principle with fire. When I would blow through the straw, it would look like the flame would come with me, because it did. I would change its position because it would want to go towards the low pressure that I was causing by blowing. The flame's largest height was 1.5 centimeters, and it could move up to 1.5 centimeters in each direction, east or west, depending on where I blew with the straw. Here I have attached a ping pong ball to a string, making sure there are 12 inches of string between my ball and the hand. When swung in front of the sink, the ball does nothing, but when the water is turned on, its fast speed creates a low pressure, causing the ball to stay inside the water and not move. Watch. Here, a similar thing happens as did with the cans. I'm using the blow dryer to push a steady amount of air between the two balloons, causing low pressure. Then, the two balloons go into that low pressure and connect with each other. They stay there until I change the place of the airflow, or until I stop the airflow completely. Daniel Bernoulli was born in the Netherlands. He was born into a family of mathematicians. Daniel published his first mathematical work in 1724 with Goldbach's assistance. They called it mathematical exercise. The first part described the game of Pharaoh and is little of importance other than showing that Daniel was learning about probability at this time. The second part was on the flow of water from a hole in a container and discussed Newton's theories, which were incorrect. Daniel had not solved the problems of pressure by this time, but again, the work shows that his interest was moving in this direction. His medical work on the flow of blood and blood pressure also gave him an interest in fluid flow. The third part of the mathematical exercises was on rhoticity differential equation, while the final part was on a geometry question concerning figures bounded by two arcs of a circle. Daniel Bernoulli did many great things, including win the grand prize of the Paris Academy 10 times, wrote a book, defined the simple nodes and frequencies of an oscillation system, showed the measurements and movements of strings of musical instruments are composed of an infinite number of harmonic vibrations, discovered how to measure blood pressure, and worked with hydropneumatics. I think Bernoulli was more than just a mathematician. He was a scientist. He was a medical enthusiast. He was almost like a philosopher. Here are some of his quotes. All birds need to fly are the right-shaped wing angle. Nature tends to act in the simplest way. The determination of the value of an item must not be based on its price, but rather on the utility it yields. The price of the item is dependent only on the thing itself and is equal for everyone. The utility, however, is dependent on the particular circumstances of the person making the estimate. Thus, there is no doubt that a gain of 1,000 ducats is more significant than a piper than to a rich man, though both gain the same amount. It would be better for the true physics if there were no mathematicians on earth. There is no philosophy which is not founded upon knowledge of the phenomena but to get any profit from this knowledge, it is absolutely necessary to be a mathematician. I'm Madison McCormick. That was my video on Bernoulli's Principle. And I'm going to leave you with a quote one great man said. Always.